The Sentinel-1 radar arrays have just confirmed a structural reality that scientists once classified as a century-away scenario. For centuries, Antarctica functioned as a frozen monolith, a thermal benchmark for the planet. But that insulation has failed. The continent is not just melting, it is experiencing a catastrophic, irreversible mechanical breakdown. The latest circumpolar metrics indicate a terrifying reality. Exactly 23% of ocean-reaching glaciers across the continent are undergoing aggressive, non-linear retreat. This is no longer a surface-level melting trend. It is the rapid Greenlandification of the southern continent. We are witnessing the mechanical failure of the planet's largest freshwater reservoir. But to map this breakdown, you must delete the surface weather data from your models. The collapse is not happening in the freezing air above. It is driven by fluid dynamics, vector geometry, and structural mechanics occurring kilometers beneath the solid ice. Throughout the late 20th century, structural models treated the Antarctic ice sheets as static geological features. Because surface temperatures regularly drop below -50 degrees Celsius, the consensus assumed the ice was locked. Early satellites only measured the surface, ignoring the subglacial boundaries. It was a fatal monitoring error. To expose the true systemic instability, the latest sub-ice sounding radar data was analyzed and ran through high-fidelity structural engineering simulations on massive vertical ice cliffs. What was found was not a static foundation, but an active combat zone. How does a frozen continent, miles thick and locked in sub-zero temperatures, begin to shatter from the inside out? You must isolate the primary variable, the grounding line. This is the precise high-pressure boundary where the inland ice sheet loses contact with the solid bedrock and begins to float on the ocean as an ice shelf. The grounding line dictates the structural integrity of the entire continental system. As long as this boundary remains pinned to the rocky ridges on the seafloor, the floating ice shelf acts as a structural buttress. It generates the extreme mechanical resistance needed to hold back the multi-kilometer thick inland glaciers from sliding into the sea. But physics forces a brutal contradiction. The very ocean that stabilizes the shelf by floating it is also its primary destructor. Warm, high salinity ocean currents are currently infiltrating the subglacial grounding zone under immense hydrostatic pressure. This water melts the glacier's root from below, forcing the grounding line to step backward onto inland terrain. Think of the ice shelf as a heavy stone retaining wall holding back a steep, massive hillside of mud. If you spray a high-pressure fire hose directly at the very base of that stone wall, you wash away the structural footing, you eliminate the friction. The entire stone wall slumps forward and the millions of tons of mud behind it rushes into the gap instantly. When the grounding line retreats, the ice loses its physical grip on the rock. Look at the empirical data. Updated circumpolar maps verify that grounding lines in the Amundsen Sea have retreated inland by up to 42 kilometers over the last 3 decades. The immediate consequence is a total loss of basal shear stress. Unanchored, the inland ice stream accelerates, dumping devastating amounts of mass into the ocean at double its baseline velocity. But what happens when the bedrock beneath the retreating ice doesn't slope upward to slow it down, but actually slopes backward into a deep subterranean bowl. The structural hazard intensifies exponentially. This is a structural trap known as Marine Ice Sheet Instability or MISI. In standard alpine glaciology, bedrock rises as you move inland. This acts as a natural brake against ice retreat, but across the West Antarctic basin, the Earth's crust behaves differently. The bedrock is a reverse slope gradient. It is a vast, dark basin that plunges thousands of meters below sea level, sloping downward towards the core of the continent. The match demands an explanation. As the warm ocean water drives the grounding line backward down this reverse slope, the ice enters deeper and deeper water. In deeper water, the vertical face of the ice sheet at the grounding line becomes substantially thicker and heavier. Glacial physics dictates that solid ice discharge across a grounding line is entirely non-linear. Picture a heavy brick resting on a mechanical ramp. If the ramp slopes upward, pushing the brick backward actually increases its stability because gravity is working against the movement. But if the ramp slopes downward, the rules change. The moment the brick slides back even a single inch, the increasing downward slope takes over. Gravity accelerates the mass down the ramp without requiring any additional pushing. Once a grounding line passes the topographic crest and enters a reverse slope basin, the retreat becomes entirely self-sustaining. The geometry of the basin transforms the ice sheet from a static frozen block into a runaway gravitational engine. The ocean is violently melting the root of the ice sheet from below. But what happens when rising temperatures simultaneously attack the ice from the sky? The destruction is not confined to the subglacial route. Rising air temperatures generate widespread surface meltwater pools across the ice shelves. This triggers hydrofracturing, the rapid physical destruction of ice via hydrostatic pressure. In its liquid form, water is roughly 10% denser than solid ice. When surface meltwater drains into microscopic structural crevices, it fills the void. Because water is functionally incompressible, the sheer weight of the water column exerts immense lateral pressure against the internal walls of the crack. The fluid acts as a hydraulic wedge. Imagine driving a steel wedge into a wooden log and then placing that wedge under a multi-ton hydraulic press. The downward force does not slowly wear the wood away. It splits the entire log completely in a fraction of a second. The water forces the fracture downward through kilometers of solid ice in a matter of hours. When an ice sheet collapses via hydrofracturing, it exposes a bare, vertical marine ice cliff directly to the ocean. This brings us to the ultimate limit of ice mechanics, the 90-meter structural threshold. Solid ice possesses a definitive compressive yield strength. When the structural engineering simulations of this exact catastrophic collapse on a 90-meter vertical ice cliff was done, analyzing the internal gravitational stress and failure vectors, the data was absolute. If a vertical ice cliff stands taller than roughly 90 meters above the sea surface, the sheer weight of the unsupported ice column exceeds the structural capacity of its own base. The foundation violently shatters under its own weight. As the outer cliff faces collapse into the sea, it exposes an even taller, thicker column of ice directly behind it, which immediately exceeds the yield threshold and collapses in a runaway, unstoppable sequence. With millions of tons of ice collapsing into the sea, Where is the ocean getting the thermal energy to keep melting the deep grounding lines? The massive influx of fresh water from these collapsing ice shelves alters the surrounding oceanography. It initiates the ocean stratification paradox. Standard ocean circulation relies on cold, dense, hypersaline water sinking near the Antarctic coast. But fresh water is significantly less dense than salt water. The melting ice forms an unyielding, floating freshwater lid across the entire surface of the Southern Ocean. This physics forces an immediate, devastating feedback loop. First, the freshwater lid completely blocks the normal, vertical mixing of the ocean column. Because of this, the freezing atmospheric air is prevented from cooling the deeper ocean layers, which finally leads to the warm, hypersaline circumpolar deep water remaining permanently trapped at depth. Insulated beneath the freshwater surface layer, this warm ocean current acts as a subglacial blowtorch to a deep-seated glacier resting at a temperature of -20 degrees Celsius. Ocean water entering the subglacial cavity at a mere 1.5 degrees Celsius functions as an immense thermal plume. It delivers continuous, high-efficiency thermal energy directly to the unanchored grounding line, accelerating the melt regardless of how cold the surface air gets. Look closer at the architectural blueprint of the West Antarctic ice sheet. The entire system has two primary structural pins, the Thwaites Glacier and the Denman Trench. Thwaites is a marine terminating ice mass the size of Great Britain. It acts as the mechanical plug for the entire West Antarctic basin. Satellite altimetry data tracks rapid internal thinning exceeding miles inland. By 2066, the ice discharge from Thwaites alone will equal the baseline mass loss of the entire continent. A complete structural failure of the Thwaites plug will unlock the backward sloping interior basin. This event projects an irreversible 65 cm increase in global sea levels, triggering the MISI mechanism across the remaining sheet, dictating a total sea level rise exceeding 3 meters by 2070. Antarctica is no longer a passive witness to global thermal changes. The mechanical limits of ice and the reverse slope geometry of the bedrock have transformed the continent into an active driver of global coastal real estate reconfiguration. The real strategic challenge for the next 50 years is not predicting the pace of atmospheric warming, but calculating the precise structural yield strength of vertical ice cliffs. If our engineering models are underestimating the velocity of hydrofracturing, our current global coastal defense expenditure are mathematically useless. This leaves global governments with a terrifying engineering dilemma. If the marine ice sheet collapse becomes unstoppable once the grounding line passes the reverse slope crest, should we waste trillions building local coastal seawalls, or must capital immediately be redirected towards high-risk, unproven geoengineering projects designed to physically pin these grounding lines from the bottom of the ocean? We will meet in our next video. Until then, stay analytical and stay curious.